Yeah, I don't know Mac. Yes, thank you very much, Peter Sarnak, for inviting me to speak here. And I also want to thank Marvin Knopp for being here. If not for him, I don't think I would have much to say about Niebuhr integrals and Mach automorphic forms. Anyway, he's here to keep me honest. Hopefully not too honest. OK, so I hope you like classical material, because a lot of the stuff I will have to say will be rather classical. And I'll spend most of the time discussing Niebuhr integrals, since that's what I know best. And toward the end, so please be patient, I will discuss Mach automorphic forms. So let me put up, hope that's legible. Is that OK? So this is the general setup that I'll adhere to. Gamma will be a discrete subgroup of SL2R. I'll assume that the area of the fundamental region is finite, but the fundamental region itself is not compact. And for simplicity, I'll assume that I infinity is a cusp, and also that negative I is in gamma. If not, it could always be a joint.
Should one think of gamma as being arithmetic or not necessarily?
Not necessarily, no. You can certainly think of that, but a lot of what I'll have to say will be true in this general scenario. The K will be the weight, and that will be an arbitrary real number, although for a lot of the talk it will be negative, you'll see. And V is a multiplier system for gamma in weight K. So if you're not familiar with multiplier systems, they're generalizations of characters. So if the weight is an integer, it's simply a character. OK, so for me, what is an automorphic form? It's a function f in this class gamma kv that satisfies three conditions. One is that f is analytic in H, the complex upper half plane. The second one is this familiar transformation behavior that f of m tau is equal to Vm times c tau plus d to the k times f of tau for all m with lower rho cd in gamma. And the third condition is the growth condition, that at any cusp, say q, f of tau is meromorphic at q. So if we look, for example, at the cusp at I infinity, this means that f will have a Fourier expansion of the following form, and going from m up to infinity. M is allowed to be any integer. So if you're used to cusp forms or entire forms, here we're relaxing that. We're letting the form blow up at infinity. And there are some parameters here. Well, we have times e to the 2 pi I n plus kappa tau over lambda. So that's the Fourier expansion, which I'll sometimes call Fe. There's a parameter lambda associated with the minimal translation matrix 1 lambda 0 1. And if you look at V of that matrix, you get e to the 2 pi I kappa. And kappa is a parameter that's being taken such that 0 is less than or equal to kappa is less than 1. OK, and I will also have occasion to look at this subspace. This is unorthodox notation, so hope you accept it. C sub m of gamma kv. This will be the subspace of all automorphic forms in gamma kv, which have order at I infinity greater than or equal to m plus kappa, and they're regular at all inequivalent, all cusps inequivalent to I infinity. OK. So that's the general setup. Now I'm going to go back in time. This is largely a historical talk. Hopefully not hysterical, but someone advised me that I should definitely put in jokes. But by the time he gave me this advice, I think it's too late. Okay, so many good things, this is well known, originated with Ramanujan, and there will be two major things that originated with him that will come up today. The first thing is the circle method, which he invented with Hardy back in 1917 for the purpose of looking at P of n, the number of partitions of n. And they showed that P of n is asymptotic to e to the a squared of n divided by b over n. And they gave a and b explicitly. You can see the constants there. Just as a quick aside, I'd like to mention that if you use calculus and some basic properties of dialogues, you can show in a very cute way that P of n is bound by e to the a squared of n divided by n to the 3/4. You could give this to an undergraduate to do with some hints. You can do this using mimicking a method of Siegel. Siegel showed this without the denominator, and if you tweak his method a little bit, you can get this result without exploiting any modularity. Okay, well, what's a key player in this work of theirs? The Dedekind eta function, eta of tau. It's very well known, defined by this infinite sum here. We know from Euler that if you take the reciprocal of the eta function, it generates the partition function, P of n. And so this is the kind of obvious way to write it. And if you want it to fit into the mold that I had in the previous slide with the Fourier expansion, you would adjust it and you go from n equal -1 to infinity. And this kappa, this 23 over 24, that's the kappa that would be associated with the multiplier system v sub, the complex conjugate of v sub beta. So v sub beta here is the complex, v sub eta is the multiplier system for the eta function, and the reciprocal of the eta function, as is well known, is a modular form on gamma 1, SL2Z of weight -1/2, and multiplier system, v sub eta bar. And the -1 just keeps track of the growth at infinity. Okay, so that's Ramanujan part 1. And many famous things flowed out of the circle method. In particular, some 20 or so years later, Rademacher had a number of results, and I'm going to highlight 4 of these results. They were all in the late 1930s, and some were refined in the early 1940s. First of all, he discovered an exact formula for P of n. This is using the circle method. I believe the story was that he was preparing lectures for the University of Pennsylvania, and he liked to work out his lectures not looking at his notes, and he discovered that if you decoupled the couple parameters, you could indeed get the exact formula for P of n. I believe a couple months later, Selberg also, at a rather young age, found this exact formula.
By the way, Rademacher believed he was wrong that he assigned his class the homework to find the error.
I guess they're still working on that.
Told me that he was in the class.
Oh, I see. I see. Wow. Maybe I'll continue. So that's one paper I'd like to mention. The second paper is that he, along with Zuckerman, found the Fourier expansion for an arbitrary modular form on gamma 1 of weight k and multiplier system V, where the weight is negative. So again, remember, these are forms that blow up at I infinity, so the weight being negative is OK. That was the circle method. A third thing that he did, he found the Fourier expansion for j of tau, famous modular invariant. Technically defined here, little j of tau is the cube of the normalized Eisenstein series of weight 4 divided by the discriminant function. We have some of the first terms here. So he found a formula using Kloosterman that involve an infinite series that involves Kloosterman sums and the I-Bessel function for j of tau. And here I think it's good to mention that he had an assist from Kloosterman. Actually, he had a double assist from Kloosterman. One was in the method pertaining to how to handle Ferri arcs. And the other one was connected with a non-trivial estimate for Kloosterman sums. So let me write a little bit on the board. I guess I'm obligated to use a greenish chalk here. I don't see white chalk. Let me see. Here. Found white chalk. So a Kloosterman sum is a sum of this form. E to the 2 pi I, say ma plus nd over c. This is nice chalk. Where m and n could be any integers, and c is a positive integer. And let's say we sum over d mod c, where a and d are reciprocals. Mod c. So that's the classical Kloosterman sum. And Rademacher definitely needed a non-trivial estimate on this, which was available at that time. I want to point out as a historical aside something which I don't think is largely known, something which I discovered when I was doing time, so to speak, at Princeton in the late 90s, that good time, that Kloosterman sums were encountered by Poincaré in 1912. In 1912, one of the last papers he ever wrote, in fact, he was too sick to check the galleys, he figured out the Fourier expansion of a Poincaré series, and he has these Kloosterman sums. Of course, he didn't do anything with it, and the sum properly should be called a Kloosterman sum, but it is interesting that the sums were indeed inevitable. Okay, the other thing I want to mention is that this exact same Fourier expansion for j of tau was found independently by Petersen, actually earlier. And the way he did it was completely different. He looked at a non-analytic Poincaré series of weight 2. He specialized it, and then he integrated. So he first found the formula for j, the derivative of j, and then he integrated it. OK, so there were those three papers. And the fourth paper, which is perhaps the most important in the context of this talk, is that Rademacher considered the following problem. If you start with the Fourier expansion for j of tau, can you prove from that the modular behavior of j of tau? And he succeeded in doing that. And the way he succeeded is he rewrote j of tau as a modified Poincaré series. And when you think of Poincaré series, usually you think of the weight as being greater than 2 to avoid convergence issues. Well, here the weight is 0, so those definitely had to be modified. It's a conditionally convergent object, and from that he succeeded in showing the modular behavior. Okay, let me put up a general theorem associated with automorphic forms of negative weight. This is due to Rademacher, Zuckerman, and Lehner, and then later on independently and differently by Petersen in the 50s. If k is a real number that's negative, and m is an integer that's negative, and we assume that big F is an automorphic form that's in this class, gamma kv, and has principal part at I infinity prescribed by this sum here, then it means that f of tau has to have a very specific form given by this finite sum. It has to be a finite sum, a linear combination of f sub nus. And what are these f sub nus? Well, for any negative integer nu, f sub nu is given by this series here, and they give explicit formulas for the Fourier coefficients of f sub nu. I didn't put these up because they get messy, but again, the key ingredients are it's an infinite series that involves generalized closed-Riemann sums. So you take that closed-Riemann sum over there and you put in a multiplier system in front of the e. And also involved I sub 1 minus k, a modified Bessel function of the first kind. So what does this say? If you have a form of negative weight and you prescribe the principal part, it has to have a certain shape. Well, you can ask about the converse question. So that's what I'd like to look at now. You can ask, does the converse hold? In particular, is f sub nu an automorphic form? It's an interesting question. And the history here is the following. That Rademacher tried, emphasis on the word tried, to show that if you start with the Fourier expansion for the reciprocal of the Dedekind eta function, you can recover the modular behavior of the reciprocal of the eta function. And he failed. Couldn't get it to work. Then there's a connection to the Institute here that in the mid-50s, I think 1956 to 57, Paul Bateman was a member here, and Selberg suggested this problem to Bateman, this problem of trying to recover the modular behavior from the Fourier expansion. Well, what did Bateman do? He went back to Urbana, and he suggested the problem to Knopp in the late 50s. And so Knopp thought about it for a while and saw that in general it would be false. Of course, does not have to be an automorphic form, and this raises the question, if it's not an automorphic form, then what is it? So in his thesis in the late 50s, Knopp resolved the case, the integer case, when k is a negative integer, the behavior of f sub nu. And then later on, about 10 years later, Doug Niebur, a student of Knopp, resolved the remaining cases. K is an arbitrary negative real number. Okay, and I'd like to discuss the work of both Knopp and Niebuhr, and in order to do that, I have to remind us, actually more setting up notation, what a Poincare series is, a cuspidal Poincare series. A big thing that occurs here is duality, and that will come out of these cuspidal Poincare series. So there are some technical issues here. Nu prime is defined. So nu is the parameter connected with f. Nu prime is defined as negative nu if the kappa, the parameter connected with the multiplier system, is 0, and otherwise it's negative nu minus 1 if kappa is greater than 0. And analogously, we have a definition of kappa prime. It's 0 if kappa is 0, and it's 1 minus kappa otherwise. Okay, well then, I'm calling G sub nu prime the Poincare series, which is a cusp form. It's a cusp form of weight 2 minus k, a multiplier system v bar, the complex conjugate of v. It's the usual Poincare series because k is negative, 2 minus k is positive, is greater than 2. There are no issues with convergence. There's no problem at all. Tau, of course, is in the upper half plane. And as I already mentioned, G sub nu prime is a cusp form on gamma of weight 2 minus k and multiplier system v bar. This is old-fashioned notation. but I suppose I'm an old-fashioned person, so I got this from my advisor and from Lehner, and that's good enough for me. So this is the notation I use for the space of cusp forms. Should be mentioned that Peterson, so these Poincare series were introduced by Peterson in the early 30s. They generalized series introduced by Poincare in 1905. And it's interesting to note that Poincare did allow the series to blow up at I infinity. He didn't restrict that. And Peterson found the Fourier expansion for these series. And I'm going to need to slightly rescale the series. So if you see, when you see G sub nu prime star, that's an appropriate rescaling for aesthetic reasons of the Poincare series.
Can I just ask a really stupid question?
Yes.
So there's a C d tau plus d to the power of some real number. That's not just in the definitions. It's not the absolute value of that.
It's not the absolute value. No, it's not the absolute value. It's not a non-analytic object, so this is holomorphic in tau. Is that okay? Excuse me?
You're worried about a branch, is that what you're worried?
Yeah. Okay.
It's okay. You have to have a branching argument, but it's okay. I mean, it's a good thing to be concerned about because for many reasons, some infamous, but it's okay here. Let me go on here. So I want to talk about some of Knopp's results from the late 1950s and early 1960s. As I said, he handled the case of negative integers. So k here is the weight. It's a negative integer. Nu is a negative integer. And that means that the dual parameter, nu prime plus kappa prime, that's what came up in the cuspidal Poincare series. That's positive. That's what makes it a cusp form. So Knopp proved the following, that what is f sub nu? Well, it's an Eichler integral. This is really around the time that Eichler integrals were first discovered by Eichler, which was in 1957. Well, this was completely independent.
Same year.
Same year.
Sitting here in paper.
And Knopp proved that f sub nu is an Eichler integral, before this name existed, on gamma of weight k multiplier system V. So what does this mean? That means it has this modular, this automorphic relation, and if you didn't have the box, well, it would be an automorphic form. But there is this period polynomial that I have highlighted in the box here, p sub m of tau nu kv. And that's a polynomial that's of degree at most negative k. So these f sub nus, remember, they blow up at I infinity. You could also do the following, another thing that Knopp did. If you take the cusp form of weight 2 minus k and multiplier system V bar, and you take this integral of it, this is a 1 minus k-fold integral. And you look at that object, which I'm calling here G sub nu prime hat, what do you get? Well, you also get an Eichler integral. Now this one does not blow up at I infinity. This is an Eichler integral on gamma of weight k and multiplier system V bar. Well, the integral operator will not change the multiplier system, so it keeps it at V bar. And G sub nu prime hat satisfies the following relation. Of course, it cannot be an automorphic form, because if it were, it'd be a cusp form. They can't exist. K is negative. It has this period, also a polynomial. Period is being denoted by p sub m hat, also of degree at most negative k. Well, you can see this if you look at this object, and it shouldn't be surprising that you would get a period polynomial. So you can ask, is there a relationship between these two period polynomials? And this, I think, is a very lovely part of the theorem. There is indeed a relationship between these two period polynomials. P sub m hat, which is a period polynomial connected with an Eichler integral coming out of a cusp form, and P sub m, if you complex conjugate tau and then complex conjugate the whole thing, they have to be equal. So it does show that cusp forms and pole forms are definitely interconnected. Okay, I want to look at some consequences of this that Knopp mentioned. So again, k is a negative integer. That's the weight. Now we know there's this duality, and we can see that f sub nu is an automorphic form on gamma of weight k and multiplier system V, if and only if the cusp form of dual weight 2 minus k and complex conjugate multiplier system is identically 0. So that's a specific result, and more generally, if you look at a linear combination of these f sub nus, you can say exactly when they would be automorphic forms, if and only if this particular linear combination of the g sub nu primes star is identically 0. And the third thing I'm going to mention very briefly here, later on with Husseini, he proved the Eichler cohomology theorem. Another thing which I'm calling Knopp's observation, because once I called it a theorem and I don't think he was happy about it, so Knopp's observation.
I changed my mind.
Oh, great. Well, too late. Next time. Knopp's observation pertaining to the Ramanujan tau function. So here's Ramanujan again. The tau of nu prime, it looks funny to call it tau of nu prime, I know, but I wanted to fit into this mold of what I've been discussing. If you let nu prime equal negative nu, so remember nu is negative, tau of nu prime, so I don't think this is so well known. Tau of nu prime is equal to 0 if and only if there exists a modular form on gamma 1 of weight negative 10 and multiplier system identically 1, with the principal part at I infinity that has just one term of this form e to the 2 pi I nu tau. So this is a very compelling reformulation of Lamer's question. So Lamer asked back in 1947, does it ever happen that tau of nu prime equals 0? And as far as I know, this is an unsolved question, which I find highly irritating. And if you have an enemy...
Selberg, he said he on a number of occasions always put this problem that the human race would never solve. Riemann for sure would be solved.
Okay, so the human...
I can give you his reason.
I'd like to hear that later. So one should move to a different planet to settle this question. Yeah, so I've spent way too much time thinking about this. And I've solved it several times, except the next morning there's an issue. I should mention that using congruences, it's not too hard to prove that it's true for a high proportion. And by work of Serre, it is known that it's true for almost all primes. So definitely progress has been made, but it stands as an open question. Okay. So now I want to go on to the work of Niebuhr. And this perhaps, well, I think it's the most important slide of the talk. It's his definition of a Niebuhr integral. Well, except for the name. I did that in the late 90s. So this is a generalization. We'll see two generalizations of automorphic forms today. The first one is what I call a Niebuhr integral. So it's the same setup. Gamma is the same type of group as before. K is a weight, any real number. If you don't like any real number, fine. Just think of integer or half integer weights. And V is a multiplier system. So we'll say that big F is in script I of gamma kV, just meaning it's a Niebuhr integral, if it satisfies the following three conditions. The first is as before with an automorphic form. F is analytic in the complex upper half plane. And the second condition, which is the key condition, there exists a cusp form, say G, on gamma of weight 2 minus k, a multiplier system V bar, okay, such that you have the following relation. So again, if we covered up the integral, it would be an automorphic form. But more generally, on the right-hand side, you subtract this integral from m inverse infinity to infinity, a vertical line, of the cusp form g of w times w minus tau bar to the negative k dw. And this here, the bar at the end just means we complex conjugate the whole thing. So it is an analytic object on the right-hand side. Okay, so that is the relation, the transformation behavior for a Niebuhr integral. And then we have the growth condition, which is somewhat technical, which you see at the end. For any cusp q, if you look at f of tau minus this integral, you can show it has a certain expansion. You can define what it means for it to be meromorphic at q. So a couple facts here. Well, it's clear this does include all automorphic forms. And also, Niebuhr proved that G is the unique cusp form associated with F. That's not so hard to prove. I think he proved it when K is negative, and then I checked it for other weights, and it's fine. The uniqueness is fine. And just as we did for automorphic forms, I want to denote the analog of C sub m, I want to call I sub m of gamma kV. This is a subspace of all Niebuhr integrals which have order at I infinity greater than or equal to m plus kappa. And for simplicity, we'll assume the regular at all the cusps inequivalent to I infinity. OK, so that's his definition. Of course, it didn't come out of nowhere. It came out of his study of these F sub nus, out of looking at this converse question that was posed to him by Knopp. So on this page, I'll summarize his results. Here, k is the weight, once again, and here we allow it to be any negative real number. Nu stays the same. It's any negative integer, which means, again, that nu prime plus kappa prime is positive. That's associated with the cusp form of dual weight. And he showed that F sub nu is a Niebuhr integral, the object that he defined. It's a Niebuhr integral on gamma of weight k and multiplier system V, and it's associated with this cusp form, this normalized cuspidal Poincare series. So that's what he showed. How did he do this? Well, he went, looked at the work of Knopp. He looked at the work of Rademacher. He went away for half a year. Disappeared. Emerged. And it was a very delicate argument involving conditional convergence, refining what Rademacher and Knopp had did. And also one of the key things, it's a simple thing, is replacing an infinite sum with an integral. But that was one of the key things. OK, he also had a decomposition result. He showed that these F sub nus form a basis for all the Niebuhr integrals. And as a corollary, he had a similar corollary to Knopp's, except for negative real weight, that F sub nu is an automorphic form, if and only if the dual Poincare series that's cuspidal vanishes identically. Of course, that's a difficult question, right? Knowing when these Poincare series vanish identically is notoriously difficult. Also connected with Lamer's question. Part B, if you look at a linear combination, when is that an automorphic form? Well, if and only if this linear combination of the G sub nu prime stars are identically 0. And then later on, recently actually, Knopp and Maui have a result on Eichler cohomology for arbitrary real weight, which extended some earlier work of Knopp. OK.
Can I just ask, does that mean you identify this space with the cohomology of some local systems? What is Eichler cohomology theorem?
I don't want to talk about it. But if you want to talk about it, Marvin Knopp will answer all of your questions. Yeah, it's just not, there's certain spaces that naturally arise in weight k and in dual weight, and you can identify them, and the difficulty is finding the mapping. But it's definitely not what I want to emphasize here. Yeah, it's not. Yeah. It's also connected with some work of Gunning, the homology stuff. Okay, I next want to discuss my work. So I forgot to mention that Niebuhr integrals, they can exist when the weight is negative and when the weight is less than 2. Otherwise, when the weight is greater than or equal to 2, there are no cusp forms of dual weight, so they can't possibly exist. So this raises the question, what about small weights? And this is what I looked at, 2 different cases. So I was a student of Knopp in the 90s. And the first case, which I'm going to discuss, pertains to when the weight is between 0 and 1. And I looked at the following object, calling it f sub nu of tau s. So here you wanted some absolute value signs. I put in some absolute value signs too, but I kept the k. So this doesn't look at all obvious, so I call this the non-analytic pseudo-Poincare series. Where did this come from? Well, if you cover up this second part here, it looks like a regular Poincare series, non-analytic. This is based on Niebur's conditionally convergent modified Poincare series. And since I like complex analysis and I like Hecke, I threw in the Hecke convergence factor, which always seems to be a good idea. So I don't have to worry about conditional convergence. Okay, this is essentially an incomplete gamma function up here. M has lower row CD. My work is on gamma 1, on the full modular group. It can be extended to other groups. The difficult issues show up on SL2Z already. Nu I'm taking to be a negative integer. Tau is as before. The real part of S is greater than k. So this integral, that's what it buys you. If we didn't have this integral, we need the real part of S to be greater than 2 minus k. But here in this weight range, it's favorable to have this. And V is as before, multiplier system. Kappa is as before, except here the translation is just 1, 1, 0, 1. The modular behavior of this is complicated. We worked out there is a period, a non-analytic period, in several variables. And f sub nu of tau s kv, well, it's analytic for real part in S, for real part of S greater than k. And it has an analytic continuation to a region including S equals 0. So to prove that, I had to use some well-known spectral theoretic work, beginning with Selberg and Rilke, and also some work of Goldfeld-Sarnak from 1983 pertaining to the growth of Selberg's Klostermann zeta function. And let me, hopefully this won't give me a trouble with time later, but let me, I think these Klostermann sums, well, I believe they're definitely the crux of the difficulty often. So what is Selberg's Klostermann zeta function? Well, you take, let me just, since I have the classical Klostermann sum here, I'll keep it. Say we take this and we sum, I guess that's big enough. We sum, say, C going from 1 to infinity. The bottom we put in C to the 2s. So this is Selberg's Klostermann zeta function. There's an analog for when you have more complicated multiplier systems. And this is not an easy function to understand. There's still some very important issues pertaining to it which are not understood. And I'd like to just mention a couple of them. Well, you mentioned the human race before, and I think that if I met an alien civilization and I wanted to test its intelligence, I would ask them, how far did you get with Kloosterman sums? Or their analog of it. If they didn't hear about it, there'd be nothing to worry about. If the civilization said, we have perfect knowledge of Kloosterman sums, I'd be very scared, very, very scared. Why? Because if you had perfect knowledge, well, you would have resolved the Linux-Selberg conjecture pertaining to growth of a certain sum of Kloosterman sums when you let C equal to 1/2. So I should mention, this has, due to work of Selberg, it has meromorphic continuation, and their pole sets are understood to some extent using spectral theory. OK, so you'd have a resolution of the Linux-Selberg conjecture. You could also have a resolution of Lamer's question based on knowing the location of certain poles of this. In addition to that, you'd solve the Riemann hypothesis, right? Because you can show, well, if you have room, you can show that this function, it's complicated, but one of the things embedded in it is the reciprocal. This is very loosely speaking. Embedded in here is the reciprocal. Well, let me put up a star. The reciprocal of zeta of 2s. So zeta of 2s plus some very complicated sums that come out of the discrete spectrum. So the result is, to be very precise here, if you could show that any one of these is analytic for a real part of S between 1/4 and 1/2, then you would have resolved the Riemann hypothesis. And you would wait a couple of years and be happy, collect some money. So I think it's a... Yeah, I say this, but I don't see how this approach could, it'd be very difficult to get this approach to work. It's just an interesting fact that if the alien race could do this, OK. Yeah, there are infinitely many poles connected with the discrete spectrum on sigma equals 1/2. One thing I'd like to mention quickly is that there's very pretty work recently, relatively recently, of Philippe Michel pertaining to oscillatory behavior of Kloosterman sums. And he even gives a quantitative result, which is very nice on the proportion. I think if he fixes, well, I know at least he handles this case. If you let m and n equal 1, he shows that and you look at the sequence as c varies, that changes sign infinitely often. These have to be real, these classical Kloosterman sums. And he shows, using some rather sophisticated machinery, that they have to change sign infinitely often, and also some very nice results as to the proportion of them. If you use work of Sally, I believe, you can get the result when m and n are equal to 1. Just the sign changes result, nothing quantitative. And for general m and n, if you use this connection using work of Selberg and maybe Kuznetsov, you can prove that it's oscillatory. OK, so now that's an aside. I'd like to get back to my work. These non-analytic pseudo-Poincare series. So the first case I handled is when the weight is between 0 and 1. That series, it makes sense through analytic continuation at the origin when s equals 0. So you can let f sub nu of tau be that specialization at the origin. And then I showed that f sub nu is indeed a Niebuhr integral on gamma 1 of weight k, a multiplier system V. And it's associated with a cusp form, which I gave explicitly. So the Niebuhr integral is between weight 0 and 1, so the cusp form here is of weight between 1 and 2. So there are convergence issues, but they can often be overcome, depending on where you are with the weight. And that's what I'd like to talk about here. If the weight is between 0 and 2/3, I found the Fourier expansion for f sub nu, and it is of the Rademacher-Zuckerman type. I mentioned before some work of Rademacher-Zuckerman pertaining to negative weight forms. And when k is greater than or equal to 2/3 and less than 1, due to convergence issues connected with a Selberg-Kloosterman zeta function, I cannot show that it's of Rademacher-Zuckerman type, but conjecturally it is. I'm sure that that's the case. And I also proved the decomposition result, that is that all of these Niebuhr integrals are spanned by the f sub nu's. And here also you have to throw in cusp forms, because the weight is positive, so we also have to accommodate cusp forms. And here, since it's SL2Z, and you're between 0 and 1, the space of cusp forms is at most one-dimensional, power of the eta function. OK, because we are on SL2Z, you can be very specific. So if we let v sub eta, this came up before, be the multiplier system associated with the eta function, on the full modular group, there are precisely 6 different possible multiplier systems that can occur in any particular real weight. And they're all given in terms of powers of v sub eta. So in 5 out of the 6 cases, if the multiplier system is v sub eta to the power 2k plus 4j, j going from 0 through 4, you can show that f sub nu has to be a modular form, because there are no cusp forms in dual weight. And the remaining case, that's what B articulates, if V is the multiplier system v sub eta to the power 2k plus 20, then when is f sub nu a modular form? Well, if and only if the nu primed Fourier coefficient of this power of eta vanishes. Well, we know that the very first, or depending, I think the way I'm counting here, the 0th Fourier coefficient of this, the first Fourier coefficient of a power of eta does not vanish, which means that f sub negative 1 is a genuine Niebuhr integral, i.e. it's not a modular form. And as a corollary to this, if we specialize yet again to the weight 1/2, we can say if the weight is 1/2 and the multiplier system, see here we're letting k equal 1/2 in B, and we get v sub eta to the 21st, then that would be a genuine Niebuhr integral, or nowadays what some people are calling Mach modular form, but way before the term existed, I believe. If and only if nu is of this shape, negative L times L plus 1 over 2 minus 1. And this just comes out of Jacobi's triple product formula for the Fourier expansion of eta cubed. OK, so that handles what I did in my thesis back in 95. And now I think I should be safe to discuss, maybe quickly, since it's rather dual, what happens in the case of small weights between 1 and 2, which I did a couple years after 95. In some ways, this case is easier. So here I looked at non-analytic Poincare series, so I didn't need the benefit of any kind of integral. So here's the, I think, rather familiar non-analytic Poincare series. This is following work of Knopp, who also looked at the case of weights between 1 and 2. And Peterson, I think, was the original person to look at such things, following the work of his advisor Hecke. M is as before, nu is as before. Here, the real part of S has to be greater than 2 minus k, but the weight is between 1 and 2, so that's good. And this transforms, as is given there, like a modular form, except for this additional factor. And if you use the same spectral theoretic tools that I had mentioned before, you can show that P sub nu has an analytic continuation to a region that includes S equals 0. Okay, well then you can specialize, let S equals 0. And then that breaks up naturally, in this case, into two pieces. G sub nu, which is the analytic piece, and is always there. And the remaining piece, which I called R sub nu, well, when it's there, it's non-analytic. Otherwise, it's 0. Okay, so by exploiting this function, I prove the following theorem. Here the weight, again, is between 1 and 2. If we look at the analytic piece, that is precisely a Niebuhr integral. That's precisely a Niebuhr integral on gamma 1 of weight k MSV. And I can write down very explicitly the cusp form of dual weight. And there are analogous results pertaining to the Fourier expansions, which I think I will skip over in the interest of time. And there's a decomposition result. Along the way, I also found some new expressions for the Fourier coefficients of powers of eta. Okay, and then again, this is analogous to the results I had before. Because of we're on SL2Z, you can be very specific as to when, for sure, it's a modular form if the multiplier system is V sub eta to the power 2k plus 4j. And we know that if it's V sub eta to the power 2k plus 20, it will be a modular form if and only if the new prime coefficient of this power of eta vanishes. And we know that G sub negative 1 is a genuine Niebuhr integral. Or, like I said, if you prefer a Mach modular form. And there's this corollary that if we let the weight be 3/2 and look at this specific multiplier system, which is the complex conjugate of V sub eta to the 23rd, then we can say that that's G sub nu will be a genuine Niebuhr integral, not a form, if and only if nu has this shape. And of course, this follows from Euler's work that gives the Fourier expansion of eta. Okay. So I said I'd spent a lot of time on Niebuhr integrals, and I have, and now I want to discuss Mach automorphic forms. In case I forget to say, I don't want to forget to say, these have been defined usually as Mach modular forms by Zagier maybe 5 or so years ago in a Bourbaki talk and then in a paper that came out. Okay, so first, harmonic Maass forms. This is another generalization of an automorphic form. So I'll say H is a harmonic Maass form if it satisfies the following conditions. Same setup, gamma kV. The first condition is that it's annihilated by this hyperbolic Laplacian, which I have up there, you can see. The second condition is that it is modular, or here I should say automorphic in behavior. And the third condition, the growth condition, is that at any cusp Q, H is allowed to have at most exponential growth in Q. So again, we're allowing things to blow up. Okay, so as far as I know, it's Brunier and Funke who coined this terminology, harmonic Maass forms. Of course, Maass forms have been around for decades, but they gave it special attention. These include all automorphic forms that I defined originally. H has to be real analytic. That's based on a rudimentary fact from elliptic PDEs. And it can be shown that H, because of these conditions, breaks up naturally into two pieces, an analytic piece and what I call a remaining piece, usually called non-analytic, but of course it can vanish. And the last fact I have here is that if you look at the action of H under this operator, so you differentiate with respect to tau bar, and then you complex conjugate that, multiply by 2yi to the k, that sends the harmonic Maass form to an automorphic form on gamma of weight 2 minus k and multiplier system v bar. Okay, so that's a harmonic Maass form. And what's a Mach automorphic form? A Mach automorphic form is precisely this analytic piece. It's the analytic piece of the harmonic Maass form. And there's this cute language, it's shadow. The shadow of the Mach automorphic form is precisely this G that gets mapped by this antilinear operator. Okay, I want to look at some examples. I don't have a ton of time. I want to look at some examples of Mach automorphic forms, and in fact, they will all be Mach modular forms. The simplest one really goes back to Hurwitz in the early 1880s, I think in his thesis. This is unorthodox notation, so I apologize if you don't like it. If you look at this here, or if you prefer just E2, this is non-normalized. If you normalize it, you get E2, the famous Eisenstein series of weight 2 on SL2Z. That is, in this new language, a Mach modular form on gamma 1 of weight 2, a multiplier system identically 1. And its shadow is a constant, 2 pi I. 2 pi I is, of course, a modular form, very important modular form of weight 0. That creates an obstruction, so to speak, and induces, so to speak, this Mach modular form. This also has different names. It's been called a modular integral with a rational period function, also called a quasi-modular form. It's also connected with almost modular forms and so forth. Let's go on to, let me mention Hecke. In the 1920s, Hecke looked at a non-analytic Eisenstein series of weight 2, and although he didn't use this language, if you complete Hurwitz's function by adding minus pi over y, you get a harmonic Maass form of weight 2 and multiplier system identically 1. It's easy to check. Another famous example is by Zagier in the mid-70s, connected with Hurwitz class numbers. If you look at this function here, that generates the Hurwitz class numbers associated with negative discriminants. Zagier showed, other people had looked at this function, but he showed the duality that arises. This language didn't exist back then also, but it fits into this mold. H, little h, is a Mach modular form on gamma 0,4 of weight 3/2 and multiplier system, the conjugate of the multiplier system for this theta function. And the shadow is, in fact, this theta function. And I think that was his main contribution here. Other people had looked at the transformation behavior of this. In particular, maybe Mordell, I'd have to check, but certainly Eichler had something on the transformation behavior, but didn't get this nice duality. So very, very quickly, I'd like to mention that I extended this in the context of gamma theta, the theta group. This is an unpublished work. I never got around to it. If you look at non-analytic Eisenstein series of weights between 1 and 2, you can get Zagier integrals that fit into this mold. So Zagier integrals, what are they? Well, they're Mach modular forms. They're similar to Niebuhr integrals. Instead of a cusp form being the dual form, it's an entire form. That's all. And there's very beautiful work. I don't know if it's come out yet. I believe it's supposed to come out in the Annals by Duke, Imamoglu, and Toth, pertaining to cycle integrals of the J function. And they have a whole host of interesting Mach modular forms in this paper. And the one thing that I would like to mention, one of the Mach modular forms is interesting in that its dual form, so to speak, is a form that blows up. And I've also done work on that that's unpublished, but in a completely different context from their context. In the context of fractional integrals and crazy things called uninhibited Poincare series, which I certainly won't be discussing today. OK, now finally, as promised, and sorry you had to wait so much for Ramanujan part 2, although perhaps Ramanujan part 2 will allow me to go over a couple minutes, I hope, because it's Ramanujan. He looked at many things, and in his last letter to Hardy in January of 1920, I believe, he wrote down 17 Mach theta functions. And why? That's what he called them. Well, why? Because when he looked at their behavior, so here, instead of tau, out of respect to him, we let q equal e to the 2 pi I tau. As q goes to a root of unity, he looked at the asymptotic behavior, and he saw that it looked very much like that of a theta function. But it wasn't a theta function. So he called it a Mach theta function. He had them of order 3, order 5, and order 7. And as an example, the one I want to focus on is f of q. It's given by this infinite series, which you can see for yourself. It's remarkable that he was looking at such things. These Mach theta functions were studied quite a bit by the likes of Watson. Selberg wrote a paper on it. Later on, Andrews did tremendous work on it. Many people, including Dyson, worked on these things. In 2001, a year before he finished his thesis in Utrecht, Zwegers made a breakthrough, a significant breakthrough, and he proved that if you take f of q and multiply it by the appropriate power of q, in this case negative 1/24th, that this is a Mach modular form. The language yet hadn't existed, but this is a Mach modular form on gamma 2 of weight 1/2 and multiplier system V, and its shadow is given by this unary theta series, which is, you can see explicitly here, it's a cusp form on gamma 2 of weight 3/2 and multiplier system V bar. Well, it's very much a Niebuhr integral, except that there's this dichotomy of history that occurred. They weren't aware of this. Zwegers was not aware of this language. How did he do this? Well, he relied heavily on certain identities. In particular, for f sub q, he used an identity of Watson. And this identity created a simpler sum, a large sum, that was easier to deal with. It also involved the identity, the reciprocal of the eta function. And Zwegers completely handled all of the Mach theta functions. He had similar results for the other 16 Mach theta functions. In fact, he did this all in 3 different ways. So it was a triumph in the etymological sense of the word, I suppose. He used identities of Andrews and Hickerson. I should say that Zwegers is or was a student of Zagier and also technically of Bruggemann. The Bruggemann, I think Zagier suggested the problem to him, but they're both his advisors. And this has created, as I wrote in my abstract, an explosion of activity pertaining to Mach modular forms by various camps. And in particular, Bringmann and Ono have been very prolific, and I'd like to mention 2 of their results. One is there was this conjecture of Andrews and Dragonet, who incidentally both were students of Rademacher. First Dragonet, then Andrews, pertaining to the Fourier expansion of f of q. Well, they found the Fourier expansion for f of q very explicitly. And how did they do this? They used a Maass, what they call a Maass-Poincare series and what I call a Niebuhr type. So Niebuhr wrote a rather famous paper, much better known than his work on Niebuhr integrals, on a non-analytic Poincare series. It's a paper that appeared in Nagoya. And I should mention quickly that that is a connection with the Institute. Niebuhr was here. Won't say he did time. He was here in the early 1970s. And Selberg suggested to him to look at this type of Poincare series that could occur if you put in a different eigenfunction that blows up. And I believe, Peter can correct me, or Marvin can correct me, that Siegel is the one who suggested this originally to Selberg, I think in 1953. So I think that's the history, and that has gotten quite a bit of attention. It's very useful. I mentioned very briefly that this can be done in a different way if you use the pseudo-Poincare series that I had looked at. You could also get at this conjecture. And another thing that I'll mention here, I will be finishing very soon, that Brinkmann and Ono, they generalized f of q to a generating function that counts the number of partitions of given size and rank. And as I'm sure you know, rank is something that was invented by Dyson, and it's very nice to have you here today. Thank you for coming. As a natural way to try to understand the congruence conjectures of Ramanujan pertaining to P of n. So Brinkmann-Ono proved that there's certain generalization, and I didn't write it down here, this generating function specialized at certain values, that it is in fact a Mach modular form. Okay, I'll put up one more slide, but I don't think I will go through it. What's the connection to Niebuhr integrals? Well, I hope by now it's clear. But if you look at special harmonic Maass forms, this is just my name for it so that I can discuss it here, i.e. those harmonic Maass forms that get mapped to a cusp form by this antilinear operator, which I had mentioned before. Well, there's a correspondence theorem between, there's a one-to-one correspondence between Niebuhr integrals and special harmonic Maass forms. In the one direction, if you assume that f is a Niebuhr integral, and you consider this auxiliary integral here, which I don't have time to discuss, if you consider this auxiliary integral, this thing is non-analytic, and it can furnish, it can be used to complete the Niebuhr integral. There's technical details, but you can use it to complete the Niebuhr integral, and you can show that the Niebuhr integral minus this auxiliary integral is indeed a special harmonic Maass form. In the other direction, I won't go through, but you can show that if you start with the harmonic Maass form, you can get, as its analytic piece, the Niebuhr integral. So what does this mean? This means, of course, that Mach modular forms with shadows equal to a cusp form are precisely Niebuhr integrals. They're the same thing. So I've run out of time, but I want to mention a couple things. One is that if you're interested in this stuff, I've written a paper with, along with Youngju Choi and Marvin Knopp that discusses its history. It also has some results that have never been published that are sketched. So I can give you this. I was going to put up what is perhaps a new proof of P of n. Since we started with P of n, I was going to show a one-line proof for the exact formula of P of n using duality. But it may be known, but I don't have time for that. So instead, I'd like to end with a quote that maybe someone will recognize here. Now, see, my glasses are good enough. Yes. So this is a lovely book, Ramanujan Revisited, that came out in 1987. And the quote is here. Whenever I am angry or depressed, I pull down the collected papers of Ramanujan from the shelf and take a quiet stroll through Ramanujan's garden. I recommend this therapy to all of you who suffer from headaches and jangled nerves. And Ramanujan's papers are not only a good therapy for headaches, they also are full of beautiful ideas which may help you to do more interesting mathematics. And that is a quote of Freeman Dyson. And I'm finally finished.